Hello, my name is David Margo, and I'm a lead civil engineer with the U.S. Army Corps of Engineers Risk Management Center. During this lecture, I will be covering the concept of effective record length and providing some tools and techniques for estimating the effective record length input that's needed for an RMC RFA analysis. Throughout this lecture, we're going to talk about the concept of what is an effective record length, why do we need to estimate the effective record length, how an effective record length is used, the value that we can get from adding more data to our analysis, and a toolbox that you can use to estimate the effective record length, along with a few of the limitations of that toolbox. Before we talk about a more technical definition of effective record length, let's start with a basic example. This slide shows two inflow records for a dam. On the left, we have a typical data set that you might see that includes some systematic data, some flow interval data for historic flood, and a perception threshold representing periods where there were unobserved flood events. On the right-hand side, we can see a data set that only consists of systematic data. It might surprise you to learn that these two data sets are equivalent statistically speaking. They have the same log Pearson type 3 frequency curve, the same distribution parameters, and the same uncertainty as measured by the confidence or credible intervals. Despite having two different inflow records, these two data sets are equivalent. How can that be, you might ask? Well, we can estimate an equivalent amount of systematic data that it would take to produce the same frequency curve and the same confidence or credible intervals as our data set. This equivalent amount of systematic data is called the effective record length. In this course and in this presentation, we are not going to go into great depth regarding the specific computations for estimating an effective record length. However, we do want to share a few basic definitions. The systematic record length is the total number of years of systematic data. The total record length is the total number of years of data to include all the systematic data and any historic flow intervals or perception thresholds. The effective record length will generally fall between these two values. We can estimate the value of the additional information provided by the historic flow intervals and the perception thresholds by calculating the average gain. The average gain measures the amount of information provided by the censored data inputs. Data with smaller uncertainty, such as a historic flow interval with small uncertainty, will generally provide a larger average gain compared to data with larger uncertainty, such as the large uncertainty that we typically see with a perception threshold. Here's another example using data taken from example 4 in the Bulletin 17C appendix. In the chronology plot on the left, we start with a systematic record collected at a discharge gauge that has a record length of 81 years. Because this record only contains systematic data, the effective record length is also equal to the systematic record length, which is 81 years. In the middle chronology plot, we have added some additional data in the form of flow intervals and perception thresholds, which increases our total record length to 146 years. However, this is not our effective record length because the additional data has some uncertainty. The effective record length for this data set is now about 110 years. In this example, we added 65 years of additional total record, but we only gained about 29 years worth of effective record length because of the uncertainty in the flow intervals and the perception threshold. Our average gain of about 0.45 means that each additional year of data that we added to the total record contributed an average of about 0.45 years of equivalent information. In the third figure on the far right, we have now added a PALEOFLOOD non-exceedance bound to the total record using a perception threshold. This increases our total record length to 840 years. The effective record length for this data set is now about 130 years, resulting in an average gain of about 0.06. The average gain is relatively small for this example. Why is that? Well, it turns out that the increase in the effective record length is relatively small compared to the large increase in the total record length that comes from the PALEOFLOOD non-exceedance bound. Despite this being a relatively small average gain, the gain in effective record length is still significant. Notice that the marginal gain in the effective record length is on the order of 20%, which is a significant increase. Now that we have a general understanding of effective record length, let's discuss how effective record length is used in a flood hazard analysis. The effective record length is used in many stochastic flood hazard models and risk analysis to model the uncertainty in the flow frequency curve. Effective record length is one of the required inputs for an RMC RFA model. The effective record length directly affects the width of the uncertainty bounds and also the expected or mean flow frequency curve in a flood hazard model like RMC RFA. The greater the effective record length is, the less the uncertainty will be that we have in our flow frequency curve. Let's take a look at how effective record length affects the uncertainty. First, an increase in the effective record length will reduce the width of the confidence or the credible intervals. Here we can see the effect of doubling the effective record length from 50 to 100 years. Second, an increase in the effective record length will also change the posterior predictive curve, which is equivalent to the mean or expected hazard curve. This occurs because of the asymmetry in the uncertainty distribution. Here you can see that doubling the effective record length shifts the mean hazard curve to the right, making it less frequent. When performing a flow frequency analysis, it is important to make your best effort to locate records of historic floods, because just adding a few bits of historic information along with the corresponding perception thresholds can add significant value to your flow frequency curve, making it worth the extra effort in most cases. Similarly, as we'll see later in this course, including quantile prior estimates based on a precipitation frequency analysis can also add significant value to your frequency curve, increasing the effective record length and reducing the uncertainty in your results. Over the next few slides, we'll walk through an example to show how additional data increases the effective record length. So for this example, we will start with a set of systematic data that has a record length of 95 years. When we add historical information to our dataset in the form of flow intervals and perception thresholds, in this example, we increase our effective record length by 20 years to a record length of 115. Next, we add some PALEOFLOOD information in the form of a paleo stage indicator as a flow interval and a paleo non-exceedance bound as a perception threshold. When this is added to our data set, we get an additional increase in our effective record length by another 160 years, resulting in a total effective record length of 275. Next, we add information from a regional skew study that's input as a prior distribution on the skew parameter in BestFit. When we do this, we get an additional 15 years of effective record length, increasing our total effective record length to a value of 290. Finally, when we add some precipitation frequency rainfall runoff analysis information as a quantile prior distribution in BestFit, we gain another 60 years of effective record length, resulting in a final effective record length of 350 years. So if you noticed as we went through each one of these examples where we added additional data, we increased our effective record length significantly and significantly reduced the uncertainty in our flow frequency curve. This demonstrates the value in combining and including all of the possible sources of data and information that we can into our frequency analysis. Now I'm going to introduce you to the RMC Effective Record Length Toolbox and give you a brief overview of how it works. In typical RMC toolboxes, the yellow cells are input cells. At the top of each worksheet, you'll see a location to put in some basic information to document your project. And then in step 1, you'll be able to enter some additional basic information to document the variable that you're modeling and the units that you're using for your frequency analysis. In step 2, we can enter the distribution parameters for our frequency curve. These would be the posterior mode values that come from our best fit analysis. In step 3, we can enter the number of systematic data in our record and the total record length. These values will be used by the toolbox to estimate our average gain. Next, in step 4, we need to enter the confidence interval that we want to use for the effective record length analysis. This will typically be the default 90% credible interval from our RMC best fit analysis. Next, we can select whether we want the software to estimate the quantile variance for us, or if we want to input our own quantile variance estimates. Since best fit does not output the quantile variance, we will usually select the calculate option. The toolbox is set up so that you can easily copy and paste a set of AEP values along with the corresponding upper and lower credible interval values from our RMC best fit analysis directly into the spreadsheet. However, it is important to always use the paste special option to avoid changing the spreadsheet formatting. When the calculate option is selected, the variance column can be blank. Here's an example of the default tabular results from a typical RMC best fit analysis. I've highlighted the AEP along with the upper and lower credible limits. In RMC best fit, you can select the data from this table and copy it to the clipboard. The data can then be pasted directly into the toolbox using the paste special option in Excel. Since we are typically most interested in the rare to extreme flood events, you should typically only select AEPs that are less than about 0.1 or less than the 1 in 10 year event for an effective record length estimate. In step 5, we have a couple formatting options. The first number is the number of decimal places that will be used to reformat the upper and lower confidence limit values from step 3 that were copied in from our RMC best fit analysis. For example, entering a value of 0 will reformat the flow values to show as an integer. We also need to enter the number of significant figures for the effective record length results. In most cases, 2 or 3 significant figures should be sufficient for an effective record length estimate. Step 6 includes some additional advanced simulation settings available to the user. The default values shown here should be adequate for any typical analysis. The user does not need to change these values. In step 7, we get to run the analysis to calculate the effective record length by clicking on the ERL button. Macros must be enabled for this to work, so if the macros are not enabled on your machine, they can typically be enabled by clicking on the Enable Content button. The simulation can take from a few seconds to a few minutes to run, and when you're done in step 8, you will see the results of the analysis. The first table you will see reports the average effective record length calculated over all of the AEPs that were entered by the user back in step 3. This is the value that you will typically use as the input to your RMC RFA model. The effective record length, however, will be different at each AEP value, so the coefficient of variation can give you an indication of how much variability there is in the effective record length over all of the AEPs. The average gain gives you an indication of the value of the additional information that you gained from including the additional flow intervals, perception thresholds, regional skew, and any quantile prior information. Also in step 8, you will see a table that reports the effective record length and average gain at each annual exceedance probability. The average effective record length for this example was 117 years, but notice that the effective record length at the 1,000-year return period is 148 years, and the effective record length at the 20-year return period is 101 years. The other bit of information that will be produced following a simulation is the quantile variance. When the ERL is computed, the calculated quantile variance will be populated in the table in step 4. Now let's take a brief moment to highlight some of the limitations of the toolbox. It mostly comes down to some fundamental differences between the frequentist and the Bayesian statistical paradigm. The effective record length toolbox and the current version of RMC RFA are based on the frequentist paradigm and the associated concepts and methods. However, RMC Best Fit uses a Bayesian statistical paradigm, and thus there are some limitations when estimating effective record length using the toolbox. We won't go deep into the theory of this, but suffice it to say, it's like the idea of trying to fit a square peg into a round hole. So why do we go ahead and do it? Well, every model has limitations. The main reason we need to do this is because the current version of RMC RFA and many other similar stochastic flood hazard models use effective record length as the input parameter to model the uncertainty in the frequency curve. A primary objective of the process we are doing is to make sure that the effective record length we select gives us good and consistent results between the RMC RFA analysis and the frequency curve that we computed in RMC Best Fit. So in many cases, it's not a big deal, and estimating effective record length for an RMC Best Fit analysis will turn out just fine. However, here's one example showing the limitations of the toolbox. This example uses data taken from example 3 in the appendix of Bulletin 17C. This data set has a systematic record length of 57 years and a total record length of 87 years. When we perform an RMC Best Fit analysis on this data set and plug the results into the effective record length toolbox, we should get an effective record length estimate of about 70 years. Now let's compare the results we would get from an RMC RFA analysis using this effective record length and compare it to the results we have from our RMC Best Fit analysis. In this figure, we can see the lines plot the results that we would expect to get from an RMC RFA analysis using the effective record length of 70 years. And the symbols represent the results we already have from our RMC Best Fit analysis. You can see that the results are reasonably similar, but they don't quite exactly match. So we might want to achieve better agreement between the RMC Best Fit results and the RMC RFA results. To do this, we can make manual adjustments to our effective record length estimate. So what adjustments might we consider to our effective record length estimate to achieve better agreement between the Best Fit results and the RFA results? In this example, we have manually adjusted the effective record length estimate using a guess and check approach until there is a good visual agreement between the Best Fit predictive curve and the RFA expected curve. We don't need to be very precise with this analysis. A visual check is usually going to be sufficient. After several trials, we can see that an effective record length of about 50 years provides a better match to the Best Fit predictive curve compared to our original estimate of 70 years. Also notice that the agreement improved at the upper credible limit. However, you can see that things got a little bit worse at the lower credible limit. In most cases, it is not going to be possible to get good agreement over all of these curves, so we must choose which curve we would like to match the best. A good rule of thumb is to match the posterior predictive curve from the Best Fit analysis to the expected curve from the RFA analysis. Strictly speaking, this new estimate of 50 years is not really an effective record length estimate, so we are going to call it a pseudo effective record length estimate. This is the value that we would want to use in our RMC RFA analysis. Future versions of RMC RFA will address this issue and eliminate these limitations that come with the RMC toolbox. During this presentation, we learned that effective record length is commonly used as an input parameter to model the uncertainty in a frequency curve. We also learned that as the effective record length increases, the uncertainty in our frequency curve will decrease. We learned about the RMC effective record length toolbox that you can use to develop estimates of effective record length for your flow frequency curves. We also discussed a few of the limitations of using this toolbox. To wrap things up, we learned that when it makes sense to manually adjust an effective record length estimate, we will typically want to try to get good agreement between the RMC best fit posterior predictive curve and the RMC RFA expected curve. This concludes the presentation on effective record length for your use with an RMC best fit and an RMC RFA analysis. Let us know if you have any questions.